Good morning, everyone. Today I am pleased to present our research entitled A Multidimensional Functional Assessment Index for Sit-to-Stand Movements Based on Pose Estimation and XGBoost. The core idea of this study is to integrate computer vision and machine learning to develop a low-cost, interpretable, and practical functional movement assessment tool. Declining lower limb function is highly associated with falls, sarcopenia, and frailty in older adults. Among various functional assessments, the Sit-to-Stand STS test is one of the most widely used clinical evaluations. However, conventional assessment methods have three major limitations. First, manual timing is prone to human error and inter-rater variability. Second, assessment based solely on completion time cannot reveal whether the movement is smooth or whether compensatory behaviors are present. Third, many existing solutions require professional personnel or expensive equipment, such as inertial measurement units, IMUs, or force plates, making large-scale deployment and home-based monitoring difficult. Therefore, we aim to develop a more comprehensive and accessible assessment approach. The primary objective of this study is to establish a multi-dimensional, real-time, and interpretable framework for sit-to-stand assessment. Our main contributions are threefold. First, we integrate media pipe pose with 5 key biomechanical features. Second, we introduce machine learning to automatically derive feature weights, thereby enhancing assessment objectivity. Third, we adopt an edge computing architecture in which all computations are performed locally, ensuring both privacy protection and real-time performance. Our system is built entirely on a front-end web architecture using HTML5 and WebRTC. No video data are uploaded to the cloud, ensuring complete protection of user privacy. The hardware requirement is minimal. Only a single side view camera positioned approximately 2 to 3 meters from the participant. The workflow consists of 4 stages: video capture to media pipe pose, estimation, to feature extraction, to machine learning evaluation, and score generation. All computations are executed locally, eliminating network latency and privacy concerns. We extract 5 critical indicators to comprehensively characterize sit-to-stand performance. 1. Time efficiency measures task completion time and reflects functional lower limb strength. 2. Angular velocity represents joint movement speed and neuromuscular control capability. 3. Movement smoothness jerk index evaluates motion continuity and identifies abrupt movement patterns. 4. Trunk flexion angle reflects momentum transfer strategies and balance control. 5. Hand assistance detects compensatory behavior resulting from insufficient lower limb strength. Together, these 5 features cover movement efficiency, motor control, smoothness, balance, and compensation, providing a far more comprehensive assessment than time-based evaluation alone. Our machine learning framework consists of 2 stages. The first stage is unsupervised labeling. We employ k-means clustering, k equals 3, to automatically categorize participants into 3 functional groups: high, medium, and low performance. The second stage is supervised classification. We use XGBoost to learn the relationships between the extracted features and functional performance levels. The model demonstrates strong performance: 5-fold cross-validation accuracy, 91.3%. External test set accuracy, 88.7%. F1 score, 0.90. These results indicate good generalization ability and robust feature representation. We propose a novel assessment metric called SSI-XGB. The scoring formula is defined as SSI-XGB equals the sum of WI times SI, where WI represents the feature weight automatically derived by XGBoost. Psi denotes the normalized score of each feature. The total score ranges from 0 to 100 and is classified into 5 levels. 85 to 100. Excellent, outstanding movement quality and efficiency. 70 to 84. Good. 55 to 69. Warning. Lower limb training is recommended. 40 to 54. Alert. Regular monitoring is advised. Below 40. High risk. Professional clinical intervention is recommended. Each score range is linked to corresponding clinical recommendations, enhancing practical applicability. A total of 120 participants aged 18 to 75 years were recruited for validation. The results show. Motion detection accuracy reached 96.7%. Timing errors for standing and sitting transitions were only 82 milliseconds and 97 milliseconds respectively, which are clinically acceptable. Regarding real-time performance, on desktop computers, the system achieves 25 to 30 frames per second. On an iPhone 12, performance remains between 20 to 25 frames per second, ensuring smooth operation on mobile devices. Furthermore, when the side view camera angle deviates by less than 15 degrees, functional classification consistency remains as high as 82%, demonstrating robustness against environmental variations. We further evaluated the scientific validity and reliability of the proposed system. Compared with clinical-grade IMU sensors, the estimated angular velocity achieved a correlation coefficient of R equals 0.91, indicating strong agreement with professional measurement devices. The intraclass correlation coefficient, ICC, reached 0.88, representing excellent reliability. For validity assessment, SSIXGB exhibited a significant negative correlation with the traditional 5 times sit-to-stand test, R equals minus 0.78. This indicates that higher SSIXGB scores correspond to faster and better movement performance. Additionally, an ablation study revealed that removing time efficiency reduced accuracy by 12.4%. Removing angular velocity reduced accuracy by 9.1%. These findings confirm the clinical significance of the proposed feature weighting strategy. In conclusion, we propose a comprehensive, real-time, low-cost, and interpretable sit-to-stand assessment system. Using only a standard camera, the system can provide professional-grade functional evaluation for home-based care, community health care, and telemedicine applications. Nevertheless, several limitations remain. For example, the accuracy of 2D pose estimation decreases under large body rotations or severe occlusions. The current dataset does not yet cover a broader range of clinical populations. In future work, we plan to establish a localized normative database, integrate explainable artificial intelligence, XAI techniques, develop long-term monitoring mechanisms to further enhance clinical applicability. Thank you for your attention. I appreciate your time and welcome any questions or comments.